Oh, it's jumping. Oh, man, look at this catch. Imagine if this fishing line, this line right here, could do more than just catch a fish. Imagine if something this thin could play a major role in fabrication and evaporating metal. So I'm about to talk about fiber lasers and how they work. Essentially, we have something called a laser source. This is what's pumping the energy into a laser head and cutting our metal. It all starts right here in that cabinet. And in that cabinet, there's a small drawer. In that drawer, there's something called pump diodes. For one of our lasers that's like a 10 kilowatt, there's 10 of these drawers. And then in each drawer, there's 10 pump diodes. So these diodes are actually pumping energy or photons through a optical fiber the size of a human hair. So those are all pumping together and then being combined through like a coupler. There's different names for this coupler combiner, but it's combining that and making it a little bit larger to get more energy. So once we're there, it's a little bit thicker. All these are pumped together. There's something called a fiber Bragg grating. So this is like a microscopic, literally microscopic etching inside the optical fiber core that changes the refractive index so that we can get the wavelength we need to cut certain materials and metals. So in my hand here, I have an example of something that our fiber lasers can do that CO2 lasers cannot. Because of the wavelength that we have on our lasers, we're able to cut things like aluminum. They're highly reflective. This is a pretty good example for precision. It has small and medium contours, corners, of course circles and sharp points, and it's pretty good. So the optical fiber I just showed you actually consists of several layers. The first layer is actually its core. This is where the fiber grating is. This core is also doped with a rare earth element, erbium. This is helping with efficiency. Actually, it makes not only the plug-in efficiency in the wall greater than a CO2 laser, but also its efficiency through the entire system. The next layer is actually a cladding layer. Just like coins have a clad, like clad D, clad P, optical fibers have a clad that offer protection. The final layer is just another protective coating. And all this is what's going on in here, which leads to cutting things like this. So something that's really interesting that took me a little while to grasp is, the light source of something that you can't see is a confusing concept. But those diodes are pumping invisible light, invisible wavelengths. Unlike this light source, which is something we can see on the spectrum. So the optical fibers are pretty much a transport of photons, right? So those diodes are all, giving their amount of energy, their amount of photons, and it just keeps combining to more and more and more watts. That's how we're able to get machines like 20,000 watts from a small source that doesn't even take up that much energy compared to something like a CO2 laser that would cut the same material. So essentially, cutting 1-inch carbon steel with a fiber laser is extremely efficient compared to a CO2 laser and faster.